We've covered indefinite integrals using the natural exponential function, so let's talk about doing definite integrals. Now, one thing you're going to watch out for when doing definite integrals with exponential functions is that often the answers aren't rational numbers. They're not like 3 over 4 or negative 12 or something like that. They're generally involve like a natural log of 7 or e to the 6th or something like that. They don't usually come out in very clean answers. They usually require a graphing calculator if you want like a decimal representation. So just be aware. So with that said, we're going to get started. But otherwise, they work exactly the same. You just have to be comfortable with this type of notation. So we have x times e to the negative 9x squared dx, and that's from 0 to 1. So what we're going to do is we're going to say, okay, I'm going to let u be the argument for e. That's pretty typical substitution. I'm going to say u equals e to the negative 9x squared. So du is, not e. Though, by the way, you could let u equal e to the negative 9x squared. I wouldn't recommend it, but you could. It's a possible way to do this problem. So, but don't. So we're going to say negative 9x squared. So du is negative 18x dx. So then we have negative 1 over 18x du equals dx. And so remember, when we're dealing with definite integrals, there's two ways to do this. One is to keep the bounds in terms of the original x, solve it like an indefinite integral, and then plug in the bounds at the very end. Another way to do it, my preferred way, is to transform the bounds as you go. The reason why I like this is because, for one, you'll often see problems actually get easier because certain things will fall out. But the next reason that it's nice is because if you end up doing multiple substitutions, which happens, then you can carry those along with you and not have to worry about kind of unfolding and unraveling it back. Anyway, just a personal preference. So when x is 0, that tells me that u is also 0. And when x is 1, u is negative 9, by just plugging in 1 here. So these are my new lower and upper bounds. So I have 0 to negative 9 of x e to the u negative 1 over 18x du. So those x's are going to cancel here, and we can pull that negative 1/18 out front. We can say negative 1/18 0 to negative 9 e to the u du. Now remember, an antiderivative of e to the u is just e to the u. So we get negative 1 over 18 e to the u from 0 to negative 9. So when u is negative 9, let me just plug in here. We get e to the negative 9 minus e to the 0. Now e to the 0 is 1. So we get negative 1 over 18 e to the negative 9 minus 1. Now this is a perfectly fine answer. There's a perfectly fine answer. But you might ask yourself what the answer should be. So let's go look at the original problem real quick. We have x and e to the negative 9x squared. Now what we know is that for e to a power, it doesn't matter what, it's always positive. So no matter what gets plugged in here, it's e to something. So that's always positive. And then on 0 to 1, x is always either 0 or positive. So I have something basically positive times positive over the entire width of the integral from 0 to 1. So since it's positive, you would expect that this answer here is some positive, right? Because if I have a positive height over a positive width, you expect a positive area. But if you look at this, you may think, well, that doesn't look positive. I've got a negative 1/18, I got a negative 1. This doesn't look positive here. But it turns out it is. And the reason is because e to the negative 9 is actually pretty small. So if you rewrite that, you have negative 1/18, 1 over e to the 9 minus 1. So if you plugged in e to the 9 in your calculator, you're actually going to get a really big number. And 1 over the e to the 9 obviously then is going to be a very small number. So if we suck in the negative and flip the signs, so make that negative and make that positive, you end up with 1/18 1 minus 1 over e to the 9. So this is probably how I would write this, or I would either write it as e to the 9 minus 1 over 18 e to the 9. That's another way to write that. Just getting a common denominator and pulling in the 18. And what you'll find is that this is still a positive number, although it's fairly small. Okay, anyway, just wanted to kind of put that out there. This next one, so again, on this one you should expect positive because 1 plus e to something is positive. E to something is positive. So you have positive height over positive width. So you should expect a positive result. So it's always good to develop that intuition so you can look at something and go, that doesn't seem right. Really helps you out. Anyway, let's keep going. So in this one, I could take u to be like that 3x. That would be a way to do it. But instead, let's take that whole denominator, 1 plus e to the 3x. So du, the derivative of 1 is 0. The derivative of e to the 3x, it's like e to the some number times x, is 3 e to the 3x dx. So we can rewrite it like that so that we make sure we get cancellation. And then we need to get new bounds. So when x is 0, u is going to be 2 because e to the 3 times 0 is e to the 0, and any number to the 0 except for 0 itself is equal to 1. 0 to the 0 is this whole big undefined arc. You can look on the internet about it and you'll see a lot of fighting. But anyway, e to the 0 is 1, so that's 1 plus 1, which is 2. Now when x is 2, things get a little more squirrely. We get that u is 1 plus e to the 6th. There's really not a nice way to simplify that because e to the 3 times 2 is e to the 6th, and that doesn't combine nicely with 1. It's just 1 to plus e to the 6th. So with that said, we now get an integral from 2 plus e to the 6th So we get that. We get 3 e to the 3x over u times 1 over e to the 3 times e to the 3x du. So those e to the 3x's vanish. They destroy each other. And we can pull that 1/3 out front. We can say, okay, now I have 1/3 from 2 to 1 plus e to the 6th, 1 over u du. Now hopefully you recognize that, 1 over u du. Well, that's a natural log. The antiderivative of that is a natural log. So I get 1/3 the natural log of u from 2 to 1 plus e to the 6th. So then we get, that's 1/3 natural log of 1 plus e to the 6th minus natural log of 2. But the cool thing about natural logs is we can exploit those properties. Remember, we have natural log of a minus natural log of b. We can combine that into a single expression. 1/3 natural log 1 plus e to the 6th over 2. Which is fine. This is probably a decent enough answer. But if you wanted to go even further, you can apply another property. We can pull that 1/3 up. We can say natural log of 1 plus e to the 6th over 2 to the 1/3. And remember that the 1/3 power is a cube root. So we have the natural log of the cube root of 1 plus e to the 6th over 2. And this agrees with what we would expect here. The reason why I believe that is because e to the 6th is positive, 1 plus e to the 6th is positive, Dividing by 2 keeps it positive. The cube root of a positive number is positive. And it's not only that, it's also larger than 1, because e to the 6 is way bigger than 1. So dividing by 2, you're still going to be bigger than 1. And then the natural log of this is going to be positive, which agrees with that. I mean, it's this very rough intuition there, but it's something. If this came out somehow negative, we had to have done something wrong along the way. So this is kind of a general overview of definite integrals, and hopefully this has been instructive for you.